Hello, everyone. Welcome back to Grade 12 University Physics here with Mr. Stone. So, all right, so let's take the natural extension here of our quantum mechanical talk and start talking about atomic physics. How do atoms behave? Right, because atoms are defined by their electrons. Electrons are the clouds that exist around them. The nucleus really does nothing to do with how atoms behave because they're so small. Nucleus is that tiny little grain of sand in the middle of it. They're the way that they physically interact with each other is completely defined by their electrons. And electrons, because they're so small, right, 10 to the negative 31 kilograms, they have to behave according to the laws of quantum mechanics. And things get strange. They don't behave in this typical deterministic way. We have to start dealing with probabilities. Right? If you remember, when we take an atom and you try to squeeze it down, right, electrostatic attraction between the electron and the proton want it to squeeze together, and no problem there. But then at some point they squeeze together too much, and because of their tiny size and because of the tiny weight, they start being affected by Heisenberg's uncertainty principle. So we start constraining their position, their velocities become unstable. So we have to start, wiggling around, and we start losing track of where they are, and they start smearing. Instead of acting, in this deterministic way, they end up becoming a probability distribution. Right, and these were the pictures that I showed you of what these probability distributions sort of look like, and they're different shapes. We have these spherical ones, these dumbbell-shaped ones. This one even looks like a donut in 3 dimensions, and it's all because of this inability to measure two things at once. Right, that's Heisenberg's uncertainty principle. Right, this is what this equation really says. If we're trying to observe position and momentum at the same time, the uncertainty between them is non-zero. It's close to zero. It's almost zero. 10 to the negative 34 is pretty close to zero. But it's not zero. So really, it does start to matter when masses get close to 10 to the negative 34 or 10 to the negative 31, like an electron. Okay, and then these probabilities, everything becomes guided by probability. Right? So all these physical characteristics of electrons at these small sizes, right? And electrons are important because electrons define chemistry, right? Chemistry defines biology, and biology defines psychology, and blah, blah, blah. So so these electrons and the way that they interact with each other is incredibly important to everything, right? So all of the physical properties like position, momentum, energy, and stuff all become determined not by what we are used to, but by probability. Right? And this famously, because like Einstein at this time, the beginning of the development of quantum mechanics, had a very famous quote, and he said that God doesn't play dice. He didn't like the idea of using these probability distributions. He thought it was cheating, and that he said God doesn't play dice, and in fact he was wrong, right? All this stuff is just probabilistic. Now, to understand these in an analytical fashion, right, how these probability amplitudes, we call these things, this wave function here, the probability amplitude psi, it's a vector here of, it's not a vector, sorry, it's dependent on the xyz and the time. This psi here, it has to satisfy this Schrodinger equation. This is the time-dependent Schrodinger equation. And as you can see, the mathematics here is way too complicated for us. This is a differential equation, a partial differential equation, which, interestingly, this is what a differential equation means. It's a scary word. It just means it's an equation of rates. So this is the rate of change in time is equal to the rate of change in space, or the rate of change of the rate of change. It's squared, right? So it's like the acceleration of this thing. Well, not really the acceleration. Whatever. The rates are related. Okay? The rate in of change with respect to time, the rate of change with respect to position, are related. And then there's this other term here, which depends on the potential. So this is a differential equation, and you can take entire university courses on solving differential equations. Now, what's interesting about them is some of them don't even have solutions. They don't have analytical solutions, which is a strange thing for you guys, because we always think of math as having an answer. But sometimes we don't even have an analytical answer, and we have to come up with simplified ways of doing it. And that's even the frontier of physics, especially in things like looking at protons, how they interact, how the quarks inside a proton interact. That's even more difficult, and we have no solutions for that. We have to use supercomputers to try to solve them. So we have to simplify things down. And we're going to take a very, very simple approach here. We're going to use what we call the semi-classical approach to atomic physics. When I say atomic physics, that means how do atoms interact with each other? Okay, atoms meaning electrons, because the electron clouds is all we care about. So really we're trying to look at how do electron clouds form. So we're going to simplify things down, and we're going to go to hydrogen. Hydrogen is the simplest atom, right? Because it's one proton and one electron, and that's it. And what makes that simple for us is that we don't have to worry about how electrons actually interact with each other. In larger atoms, they have more electrons, and they do weird things to each other. They screen each other, they interact with each other. And we don't want to have to worry about those terms. All we want to worry about is the electrostatic potential term between the proton and the electron. So when they were studying hydrogen, an interesting discovery was found. Well, this was most gases. But if you take a gas and you put a high current through it, so high voltage across it, like 5,000 volts or something like that, through the gas, it'll glow. This is how neon lights work, how your fluorescent lights work. So it glows in a very peculiar way. It doesn't glow like, let's say, something, a black body. It glows only in very specific wavelengths. If you take the light from, let's say, glowing hydrogen, and you put it through a diffraction grating or a prism or something that splits up the light, something that reflects light at different angles for different wavelengths, disperses it. Chromatic dispersion, we call this. You can split it up into its different components. And it only has very distinct components. This is an experimental result here of what we call the emission spectrum of hydrogen. And when they were studying this, they found an interesting relationship. This is purely from experimental results. There's nothing physical in this. But the relationship between the wavelengths in here is given by this equation, where n lower or n upper, these two numbers on the bottom, are integers. They're only integer values. There's certain particular energy levels that exist and transition between those energy levels that exists. And they're integers. They're discrete integers for each particular wavelength. Now, how this is interpreted in our quantum mechanical view is that the hydrogen has energy states, allowable energy states, where electrons can exist. You can think about it like a shelf, basically. The electrons can exist only on particular shelves of energy. And when we excite them, the electron jumps to a higher energy state, to a higher shelf. And then it spontaneously comes down. And as it comes down, it's going from a higher energy to a lower energy. So it has to, give off some energy because of conservation of energy. When it goes from the higher to a lower, it gives it off. And it gives it off as light. It releases a photon of light. So these quantized energy states, which we're going to call n, are the only allowable energy states that this hydrogen electron can exist at. And when it jumps down, from one of these allowable places, it gives off a particular energy for that particular difference between the shelves. And it's all becomes made a formula by a constant that sets it all together. This Rydberg constant here. Okay, and if we plug in some numbers, right? If we're going from the down to the first, what we call the ground state, N1, this lower N1, we're always going to get this series of wavelengths in the ultraviolet. The going down to n equals 2 gives us visible spectrums, and that's what we see in this picture here. This is 656, 486, 434. That's these ones here. This is from the third shelf to the second shelf, fourth shelf to the second shelf, sixth shelf to the second fifth shelf to the second shelf. Okay, and then if you go down to the third shelf, that's even smaller energy differences, so that ends up being in the infrared. These are large energy differences, right? Because there's a big difference between 2 and 1, or 3 and 1, 4 and 1. These all end up ultraviolet, so higher energy. The visible ones, though, are between going down to the second shelf. We can do a quick calculation here as an example. What's 6 going to look like from 6 to 2? So if I plug those numbers into my formula, I square the numbers, subtract them, find the difference, multiply by Rydberg constant, take the inverse, I get 410 nanometers. So almost ultraviolet. So this is very, very close to ultraviolet. And as you can see, what happens as we get from higher energy states, as we get up higher and higher, this term here, this second term here, when we're subtracting, this gets smaller and smaller and smaller. So the differences between the upper ones get smaller and smaller. We'll see what we mean by that in a second. You can even go backwards. Let's say if I give you the wavelength, you can plug that in. We know it's visible, right? We know this is 656. It's between 400 and 700 nanometers, so it's visible. So it has to be 2, right? This lower has to be 2. If it was above, if it was in ultraviolet, it would be 1. If it was infrared, it would be 3. So then I can plug in my values, and it works out approximately to 3. I say approximately because we only have 3 significant digits, so things get a bit weird, as this being 0.139, and then I have 0.3333. So I changed that because of because of the uncertainty or the precision of our initial value. Now let's think about this in terms of energy. We talked about these states having to exist as energy states. So what are their energies? And we can use Planck's equation here for energy. E is hf, or hc over lambda. And we can replace 1 over lambda with E over hc, and then multiply both sides by hc. And we can change, we know that this energy here is the energy of the photon given off, right? That's the energy that's released. That's the difference between the energy shelves, right? That's how much energy from the higher state, EU, subtract the lower state, EL. That's the difference between the energies, is going to be the energy of the actual photon. And we come up with this equation. So this is the energy of our light given off is equal to Rydberg's constant times Planck's constant times the speed of light times the difference here. And it works out, when you look at the different numbers that come out of this difference in energy, we end up with these energy levels for the quantum numbers n up to infinity. You can see it starts off, at 13.6 and then heads up all the way until we actually get to a point where, because that second term gets smaller and smaller, the differences between them get smaller and smaller as we head up, until they actually end up at what we call an ionization state. There's a maximum difference between the ground state and the highest one, which is where the electron is actually freed. And that's why these are negative, because these energies are negative because they're bound states. The electron is bound, right? When we talked about a potential energy of an orbiting thing, we talked about potential energy being negative because it was being held there. So we're going to use that again. These negative represent the ground state, or the bound states of our thing. So really what we care about for the photons that are given off are the differences between there. and those are going to be positive. So we know that when we approach infinity, n approaches infinity, right, we're going to end up with an ionization state, which we're going to call EI. And that's when the upper one, this ends up into infinity. And whatever infinity, this term here, when this lower number, sorry, this upper number, nu, gets bigger and bigger, this just goes away, right? That's gone. And then I can subtract the EI from, and I have this energy state. But really, I'm going to get rid of that one as well, because I'm going to want that to be the, so we can simplify our equation here, right? We can simplify it by saying that the ionization energy is 0, right? Because that's when it's being released. That's when it's no longer bound. It's now a free electron. It's been kicked off. And in that state, the upper one is infinity, so that's gone. So everything simplifies to this, which is the Rydberg constant times Planck's constant times C, which works out nicely to this 13.6 electron volts. That's where that number came from in the previous slide. And it's negative because it's bound. And n really should be, it's 1, 2, 3, and so on and so forth. Okay. And it's one of these inverse squares, which is interesting. But remember that these are discrete energies. These are these shelves, right? They get closer and closer and closer as we get to the top. And these n's are what we call these quantum numbers as we go up. And those are the energy levels. The energy states that an electron can exist at in this semi-classical view are defined by these numbers. Now, we haven't defined anything physically yet. We haven't really. This equation is purely from looking at the wavelengths of the emission spectra. Nothing in this is actually saying why. Right? There's nothing in this that says why something should be the way it is. So, to come up with this idea, Niels Bohr, famous physicist, who you've probably heard of, because remember doing in grade 9 Bohr-Rutherford diagrams, where we put the electrons on those rings. Well, those rings represent our energy levels. So, right, we put 2, 8, 8, 2, or whatever, 2, 8, 8, 18. Those shelves that I talked about are the same thing as those energy levels. So when a hydrogen electron jumps, it's actually jumping to those different rings that we drew in our Bohr-Rutherford diagrams. And that was Niels Bohr's big idea, was that the energy states in an atom are quantized. There's only certain allowable energy states. And there's only specific shelves in which the electron can exist at. And his idea was that, taking from de Broglie, right, that there's these waves, that the matter has to follow a wave equation. So working with that same idea, his thing was that, the idea at least, is that these energy states are overtones of standing waves in the atom. Okay, that's a big idea here. That's a weird thing to say. But you can think of it like in this picture here, that each of these energy states, these energy levels, 1 up through 5 in this picture, correspond to different standing waves, different orders of standing wave. And they're allowable at only 1, 2, 3, 4, and 5. Okay? And you can see here that this is 1, this goes back and forth like this. I'll show you a picture in a minute. And the reason that they're only allowable for integers is just due to what we call a continuity equation, or a boundary restriction, that the wave has to go back onto itself, right? It's a standing wave on a ring, so it has to go around in a circle. If it's not an integer, we end up with a break in the wave. Here, let me show you here. Got a little Desmos thing going. If I change my, let's go to 1. So this is n equals 1. I have this resonance on my wave. My wave is basically, think about a string. Imagine the first overtone on the string, but I take my guitar string, let's say, and I wrap it around itself into a circle. So this is how this ring has to vibrate. Now, if I change that from 1 to 1.05, you can see here that it breaks. If it's not an integer, we're actually not, we're no longer a ring, we're no longer a string or a wave or something, right? It breaks. There's no continuity there. Even if I go to 1.5, it's still, it's continuous function here, but it's no longer differentiable. It's got a pointy bit. Pointy bits are bad for physics. Okay? Physics doesn't like pointy bits. So it only satisfies it at the integers. Oh, no, there, 2. So this is now at 2. This is where that dumbbell shape comes from. So n equals 1 is an s orbital, borrowing from chemistry. Those are spherically symmetric. And then when we get n equals 2, we get p orbitals, which are dumbbell shaped. And then we get n equals 3, we get weirder things happening. Okay, and it's more complicated because it's in 3 dimensions. So this is on a ring, right? But we're actually talking about a sphere. Harmonics on a sphere, spherical harmonics. But what I just wanted to show you with this is that it doesn't work unless we get to values that are integers. So the quantization of the energy levels is based on a wavelength of the matter, this wavelength of our electron. Remember, electron doesn't exist as in an orbit. It exists as a probability. So this probability density has a wavelength. This is where things get really wonky, right? This ring represents the electron, okay? And it's vibrating in this way such that it follows this continuity equation. So we end up with this idea that the allowable wavelengths, the allowable matter waves of the electron, as it's bound in a hydrogen atom, has to satisfy this equation, right? 2 pi, because we're using radians here. So 2 pi radians all the way around. And then whatever n is what we're dividing by here. So let's say n equals 3. Our wavelength up, back to the middle, back to 0, then down, and then back to... So this is a full wavelength is a third of the way around the circle. So that's going to be 2 pi divided by 3, multiplied by the radius, which is the distance, the average distance, this red circle. Okay, if n equals 4, it would be a quarter of the way around, right? So it's going to be 2 pi times r, right? Where r is the full, is the radius here. So 2 pi c, right? 2 pi, this is equal to the circumference of our circle, right? 2 pi times the radius. So it's basically just our circumference, 2 pi r, divided by whatever n we're at, however, what fraction it is, right? If we go to different fractions, this is 7, so these are sevenths of the way around, right? N equals 5, right? This wavelength, so that would be, so let's say start here, and then it'll go around to here, and that's a fifth of the way around the circle. Okay, so we have a condition which we end up calling the Bohr quantum condition, that the wavelength has to be equal to 2 pi r n, which is the radius of the nth orbital, divided by n, which is our order, our energy state. And we know from de Broglie that that's also equal to h over mv. Or we can rearrange it to n, so the energy level n, 1, 2, 3, 4, multiplied by Planck's constant over 2 pi. This is h bar. Physicists are lazy, so they call that h bar. Is equal to mvn, so the velocity, interesting idea, velocity, of the electron in that nth orbital, and the radius of the orbital. Okay, and this is what we call the Bohr quantum condition. And this works. This gives us a working theory for how electrons exist in a hydrogen atom. So if we consider a hydrogen atom as an electron spinning in an orbit, we can use a classical approach to determine some of its characteristics of its motion. Now, remember, this is a weird idea because uncertainty kind of makes everything all messed up. Okay, but it gives us a way that we can use our classical understanding of how electrons behave and apply it to our quantum mechanical view. Right? And the electrons have to be held in place by a Coulomb force. And they're sort of orbiting with a centripetal force. This is a weird idea. They're orbiting with a centripetal force because they have mass and they're going around, and they have to sort of orbit in that condition according to this, that the orbit has to satisfy this. But remember that it's not an orbit, right? That's why orbit here is in quotation marks. But we can apply this idea of a centripetal acceleration or a centripetal force keeping it in place. Okay, that Coulomb force is sort of keeping the electron in place in this orbit, but then that orbit is then smeared out by uncertainty. Okay? So this model it's not, completely accurate. It's not, but it works. And that's the beautiful thing about it, is because it's a hydrogen, it's only one electron, it will work. And it gives us that first, theoretical approach to how atoms exist. Right? And it gives us the proper energy levels that we see. Using this idea, we can get exactly the energy states, the 1 over n squared idea. So we got that 1 over n lower, 1 over n upper, right, just from an empirical analysis of it. But using this, it actually works out, and that's part of your homework, is you're going to show that. Now, unfortunately, the problem with this model is once we get to higher, anything above hydrogen, which is everything, it doesn't work anymore because electrons interact with each other, and that causes a big problem. And the only quantization that we've thought about here is energy. There's actually more happening. We also have to quantize the angular momentum. That's the measure of how it's rotating, the energy of rotation. And also there's another thing called spin. Electrons have their own internal momentum, or angular momentum sort of, which is called spin. And I wish that they'd never called it spin, because really that kind of gives you an idea of these electrons spinning. They're not spinning. They can either be up or they can be down in their spin. And it's way more complicated than here, but it has to do with something called Fermi statistics and how we can stack elements within these energy states. Electrons, they can only exist, only one of a certain quantum state can exist in any energy state. They can't stack on top of each other. That's why you filled, let's say, the inner orbit of when we did a Bohr-Rutherford diagram, we always put 2 electrons in the first orbit because we can only put 2 electrons in that first state. There's only space for 2. It only has one quantum number, but we can put an electron that's a spin up and a spin down into it because those aren't the same. So we can put 2 into there. And this gets way more complicated than I want to talk about, but the whole point is that we're not worrying about that. Because from there we can end up worrying about all kinds of other things, but don't worry about it. But the important point is this is a great starting point for a theoretical picture of our atom that helps us understand how these atoms behave. But again, this is quantum mechanics. Things are weird, right? Even though I'm talking about things orbiting, and I'm talking about wavelengths, and I'm talking about all this stuff, it doesn't really happen. Like electron spin is a perfect thing. Electrons don't spin. They don't spin like a top. But it's a quantum number that we have to apply to an electron to give one of its properties. Okay? Because of the plus or minus half spin in Fermi statistics. But I've gone way too far. I apologize. Okay. Anyways. So really, this is our semi-classical view that kind of blends quantum mechanics and a classical view as well. Eventually, we were able to replace all this with Heisenberg and Schrodinger and all these probability densities and stuff, but it works. So using our working theory, I'd like you for homework to show me that if we end up with this formula here, this is the electrostatic potential here, right? The force, the electrostatic force is equal to K, 9 times 10 to the 9, whatever's. Z is the number of electrons in the atom multiplied by, well, yeah, that's the atomic number, multiplied by the charge. So this in hydrogen, this Z would be 1, right? Because there's 1 proton and 1 electron. So it'd just be 1 times E squared. So 1 E from the proton and 1 elementary charge E from the electron. So the two charges are E and E, so E squared, over the distance, which we're going to call Rn. So this is the what we call the Bohr radius. The size, now when we talk about radius, right? Let's call this Rn. It's a blur, really, right? But we can give this some sort of a probability density, and we say this is the maximum probability of being in there. So we're going to call that most likely place for the electron to be radially Rn. We also have our formula for our centripetal force, right? This has to be going around in some sort of orbit with a centripetal force pulling it inwards, given by mv squared over r squared, where v is the velocity in that orbit. And we can set them equal to each other. Now what I'd like you to do is to take this equation, setting the electrostatic force, which is equal to the centripetal force. If I apply my Bohr quantum condition here, I'd like you to derive an equation for the Bohr radius. Get Rn by itself. Put these two equations together, get Rn by itself, and figure out what the Bohr radius should be. Okay? I'll tell you right now, it's like 0.5 nanometers. Or is it 0.5 angstroms? I forget. It's 0.5 something. 0.5 times 10 to the negative 9 or 0.5 times 10 to the negative 10. Okay? But that's what we call the Bohr radius. That is the radius of a hydrogen, an unexcited hydrogen atom. All right? So you can put those equations together and figure that out for me. All right? To keep in mind that n equals 1, so that would be the lowest, the unexcited, the ground state, what would you call it? The ground state being the lowest state of hydrogen, and hydrogen Z equals 1. Okay? And then there's a couple more problems as well, using these formulas to calculate some of the energy states. The light that's being given off. Oh yeah, it is called Balmer. I was right. Okay. All right. Anyways, so that was a lot. Quantum mechanics is strange. Just keep that in mind. All right. Typically, if you take quantum mechanics in university, it's either a 3rd or 4th year physics class. It's pretty complicated stuff. I'm trying my best to put it into a grade 12 level and try not to get things way too complicated by frightening mathematics, but it's difficult. I apologize if I've completely blown up your brains. All right. Okay, so I'll be talking to you later. Take care.